Give me a second. Yes, this works. Okay, I work at PEX, and I have first a talk that I called extern constinit const foo, which is something that I actually recently wrote into my code base. And I just wanted a constant, which is basically my reaction when I figured out that this is what I have to do. The big difference is that actually I had an array of these. So let's talk about what we will talk about. So I will talk first about the history of how we declare constants in C++, how we do it now in C++20, a set of guidelines that you can use and follow to have reasonably painless experience. And of course, I will talk about why we can just have a goddamn constant. Why? So let's start with C++98. And in C++98, we had three options to define a constant. Number one was a macro. The other option was to have an anonymous enumerator, and then just say that one of the elements is the constant that we want. And the third option was that we would have a compile time initialized const variable with internal linkage, important. And like this wasn't much, but it worked. So let's go over them in details. First, macro. We all know this. We have to define, and then we have to say my project, the actual name that we care about, and the value. And hopefully this works. Of course, if anybody at any point ever defines the same name, we have an issue. It's the big one, right? They are big separate language from C++. They don't behave the same. They don't respect parentheses, braces, and so on. And of course, if you have, you got namespace a macro. Namespacing a macro means just adding more to the start of the name until you are happy that it will not collide with something else. And they don't have linkage. This is important. It doesn't have to be negative, but this is an important fact about them. What do I mean? So if you ever write something like this, I have my max value that I care about, which is 42, and then I want to clamp some argument that I got. And I take it by reference, the result, because stdmax returns reference, and I might be in some generic context. Then this is dangling. Okay, cool, you got the maximum, and if you needed the max value, that's it. The end. Your program has died. Because this doesn't have linkage, so after this line, the constant doesn't exist that you have taken the reference to. Now, anonymous enums look like this. This is actually a big improvement over macro because now you have namespaces. You can say, okay, this is namespace to my project. This has this obeys, braces, and stuff. Cool. But they still don't have linkage. So if you replace the macro with just an enum, same issue. You clamp your value, and if you ever run into the maximum value that you care about, it's dangling, and your life and your code ends here. So let's get to constant variables. These are much better because they actually have linkage. I can write this code, and it will be correct. Yeah, but it's subtle. But actually, this is UB, almost definitely. But at least it will not explode loudly. It will be silent, UB. Yeah, so another issue that we have with constant variables is that it's easy for them to still be constant. You write, okay, I have my constant, but I calculated with a function. It's no longer constant. It's no longer compile time constant. But because C++ is fun, we have this thing called VLA from C. So this is no longer constant initialized, but it is a variable length array. So it will compile, except now it behaves differently. Yeah, it was C++98.
Why can you compile in 98 compile?
This? Yeah. Because GCC, which is very popular, just has VLAs as extension from C.
By the time, and if you tell definitely that the variable couldn't be compiled in couldn't be compiled. Yeah, so calculation will be done like this. This variable will be located in data segment, and we will definitely run this function before main entrance. At the same time, function f would use this variable only in runtime, and the value of the case some constant is indefinite during compilation time. So I don't believe in this code.
This will compile. This is VLA, right?
What is the compiler you're using?
GCC.
GCC?
Yes.
What version?
4.8, 9, 5.0, 6.0, 7.0, 8.0.
Means it will allocate the right dynamically on the stack.
Yes.
Dynamic allocation on a stack is impossible at all.
Yes.
It's alloca.
It's alloca.
You call alloca, it bumps down the stack pointer by however the fuck.
Yeah.
Yes.
Yes.
Stack.
Yes.
Yeah.
Okay.
It's not good, but
It's how VLAs work, yeah.
Okay, I will check.
So it's not great. Let's talk about C++11. What do we get in C++11? So we get const expr keyword. And const expr keyword can be applied to variables. And in that case, they are forced to be compile time. And it also changes like how do we actually define constants. And they have to be initialized compile time, right? This is now compile error. You can't say const expr integer some constant is computed by function that's executed at runtime. That's good, but you can use const expr functions to compute your const expr variables like this. It's silly, but this will compile, and it works as you expect it to. So this is cool. But it's also very, very easy to get undefined behavior with const expr. This code, we have header, it has pragma once, it defines some constant, and it defines like function like this. Just I care about the limit of some argument that I got. And at the second that you use this header in two source files, that's ODR violation. And ODR violation is IFNDR, all colloquially undefined behavior. Yeah, this is C++11. It's not great. But we can fix this. This is the intended way of using const expr constants. You just put it into the function. Now, because it's in the function and the function is in line, the compiler has to deduplicate all the constant to ensure that there will be only one. But that's not great, right? Because we will want to use this constant in multiple functions. If we didn't want to use it in multiple functions, we wouldn't have to define it. So there are two ways around this. The first one is just don't use references. If you write your code like this, you define your own max, which doesn't take reference, only values, then you don't form reference to the constant, and this is fine. The issue is when you start forming references to this constant, which is duplicated across multiple translation units. But yes, just don't use references is doing a lot of heavy lifting in C++ because every template ever likes its const tref because that's the most reasonable generic parameter passing that you can do. But there is another way to do this. You just hide your constant into templates. You do this. By saying that, hey, this is actually like a static variable in a struct that's templated, you force the compiler to figure this out instead of you. So it will have to store this like authoritative, the storage once, it will have to figure it out for you. And then you can just give it a convenience name, which you wanted in the first place. And this is actually valid as long as it has static, so it has local linkage. And yes, I had to do this a few times before I wrote it correctly. So C++11, beautiful, isn't it? Let's talk about C++ 17, because 14 gave us much better const expr functions, right? If you remember const expr in C++11, it was basically useless. 14 is a lot better, but let's talk about 17, because 17 actually fixes a lot of the issues that we have. Because C++17 added inline variables. And inline variable is just like inline function. You get one copy in each translation unit, but then the linker is responsible for deduplicating them. And because it's deduplicated, then you don't have ODR issues. There will be just one of them. So if we go back, this is now correct. You just say, okay, it's actually inline const expr variable. This is fine, because now it still forms the reference, which is the issue, but there will be only one address in all translation units. You are fine. Great. Amazing. Let's talk C++20. C++20 added actually one new thing for variables, and that's constinit. It also added const eval for functions, but those are not relevant to this talk. And constinit variable must be static initialized. The static initialization is a technical term, which boils down to must be either 0 initialized or compile time initialized, roughly. And that's what we need. Must be during compilation, either of these two is fine. Now, that sounds very similar to const expr. So let's talk about what constinit isn't. So unlike const expr, constinit does not imply const. You can have code like this. You can say, okay, I want to initialize this squared variable to something at compile time, and then I will change it, and it is changed, right? It's not a constant, actually, on its own. And also, unlike const expr, constinit does not imply that it's usable at compile time. For code like this, I say I have constinit int a, and it's initialized. Const expr int b, it's initialized to a. No, this is a hard error. A is not usable in const expr context. Okay? Now, you can actually make it usable at compile time. You just say it's actually const int, because that's how we did constants in C++98, and it still works. But what does actually constinit do? Why does it exist? Why did we add it to C++20? And it prevents the static initialization order fiasco, right? If you have ever had the issue that you have global variables that depend on each other, then you might have run into the issue where you don't know in which order they will be initialized across translation units. Because in one translation unit, you go from top to the bottom, that's fine. But once you have linked together multiple initial translation units, you don't know which translation unit goes first. It's linker dependent, and the linker can do whatever. And it's also an optimization hint for very, very specific case. This is the example. If you have a thread local variable, then if you mark it as constinit, then you promise that it will be initialized at compile time, which actually has significant effect at the generated assembly, because this is, if you don't promise that it is initialized, the compiler has to start by checking whether it was initialized, and if not, it has to initialize it. And this will be checked every time you call the function. But if you do promise that you have initialized it, then it's just like, yep, it's easy, load, and we are done. So that's the theory. That's how C++ works. Let's look about more practical stuff. How do you actually declare constants in C++20? So what if you want to define a constant in a header? Inline const expr, always. There are very specific edge cases where plain const expr is better, but that's experts only. Use inline const expr. You don't have to care about ODR, and this is good. So it looks like this. Inline const expr, target name is some string. That's it. Good. What if you want to ensure compile time initialization, but it doesn't have to be constant? That's const init. Right? We promise that it will be initialized at compile time. The compiler checks for us. Now, by the way, one of the uses for this is that you can have classes which have const expr constructor, for example, shared pointer, but don't have const expr destructor, right? Because you can't const expr destruct shared pointer, but you can construct it. You can use the default constructor, which is empty pointer, just to make this clear. Now, more advanced stuff. I want to have a lookup table in a function, and I want to construct it at compilation time. And this is tricky. You use static const expr. Why? Well, because it will never optimize worse than if you use plain const expr. Example is here. Let's say that we have these two trivial functions, which have just small lookup arrays of mapping from indices to string views. And for the first one, we say it's static const expr array. For the second one, we say it's const expr array. It actually generates significantly different assembly. Right? This is the static const expr. You can see that we just load from the array that's somewhere. We do two loads because the first one is for the pointer, second one is for the size, because string view has two elements important, and that's it. Before that, we just had to multiply the number to get the correct address. Now, this is what you get with plain const expr. And what it is doing is that it constructs this array on the stack. It loads every single pointer for these. Pointer, size, pointer, size, pointer, size, pointer. And the last size is here. And then it returns from the table. Amazing. The reason now, for this case, this is trivial, right? Clang actually optimizes both functions to the same one. It's smarter. This is GCC. But if, for example, if you take this array and you pass it to a different function, then this is actually the behavior that you get, that you can't fix, because you have to materialize the array somewhere on the stack, and you then pass it somewhere else, right? So to reiterate, static const expr for constants in a function.
Depends if you want to materialize it or not, because when it's static, you not force, but incentivize the compiler to make explicit.
Yes.
Somewhere, but unless you're doing this array of objects, sometimes you may want to actually like inline the object, and then you want to avoid static. More probably like material.
Yes, this is actually also the answer to when is it better to use plain const expr global constant than inline const expr, because it's easier to eliminate the linkage to the materialization of plain const expr. But like it will be very rare that it's actually better for you to have plain const expr, because this is like the main use case of these lookup tables or some complex objects. And if you ever have to then load them onto the stack, well then, yeah. Now, we are getting to the part that actually started this whole talk. So what if I have a bunch of constants that I know at compile time, but I want to process them in one single translation unit. And why do I want to do this? Well, if you have some constructed variables and headers, then every translation unit that includes the header has to process them. It has to compile them, it has to run the constructors, and so on and so on. And I don't want to do this. Like I have this array of 10,000 elements of string views, and I don't want I don't want 10 translation units to construct 10,000 string views. No, that sucks. So what I want to do is that I want to still process the array. I still want to do something with these constants at compile time, but I only want to do this in one translation unit. How do I do this? In the header, I say, okay, so I have extern constinit const t of my type foo or the name. I have to say, so this is external linkage. It will be constant initialized. It will be initialized at compile time. It will be constant after initialization. I have to have my type, and then I have foo for name. And in the CPP file, I actually redeclare this as const expr. This is called initializing declaration, and it allows me to treat this variable as const expr for that single file. And you can then here you can then compute some extra information from this T, and you can store it in other variables that you export to other headers. This is useful. For example, like we are embedding pre-computed values, right, in our project. So I have array of 10,000 strings that are pre-computed by some Python script that generates the CPP file, and then I can process it in C++ further, and I don't have to teach the Python script about my business logic. This has one issue. And the issue is that there is actually different bugs in MSVC and in Clang that you will trigger if you do this. I opened both of these actually. MSVC doesn't support having constinit declaration and then the initialization declaration as const expr. Clang is just a minor issue where it gives you warning that's not true, and it tells you to fix it in a way that breaks the code. And yeah, final fun fact about this. So I have shown you the old style C++ 98 constants, right? Const int something. Arrays have to be const expr because when you dereference an array, even if it's an constantly initialized array of const t's, logically it should be constant, then the dereference is an L value to R value conversion. You are not allowed to do L value to R value conversion in const expr context. But if you declare it to be const expr instead, the array, then that's a special case in the standard as, yeah, you can do this. So some conclusion for this. Look, not even constants are easy in C++. And it took until C++ 17, between 98 and 17, that's basically 20 years, before you could make a constant variable that's actually safe to use. But since we have C++ 17, you can actually do, you don't need to know much. Just use inline const expr outside of function, static const expr inside of functions. You don't have to think about it anymore. And that's the end of this talk. Unless, of course, you are doing weird stuff like me. So, questions for this? Okay, if not, then I'll take a quick break.
Are we going to talk about plasma with this title?
Yeah. Yeah, let's talk about fun and safe math optimizations, And so what we will talk about? Well, I want to talk about fun and safe math optimizations, or fun safe math optimizations, GCC and Clang. Because who doesn't want fun and safe optimizations? So I did some research, and it turns out actually functionality flags in GCC are prefixed with F. So actually we are talking about unsafe math optimizations. And unsafe optimizations, well, those are no fun. So that's it, the end. Time to go home. No, okay, I made the most obvious joke about this, so let's actually start for real this time. What we will actually talk about is, some flags, like F unsafe math optimizations that govern floating point optimizations in the compiler, and what they will do to your code. And I will try to convince you to not use them, most of them. let's start with a quick overview. The big one and also the hidden one is fast. It sounds great, let's go fast, but it enables fast math. Let's talk about fast math. And fast math, who doesn't want to be fast? I want to be fast, but actually it enables lots of stuff. No math, no F-unsafe math optimizations, finite math, rounding math, no signaling nonce, so on and so on, and some more actually. And yeah, this is where the title of this talk comes from. But also this flag, it enables more stuff. It adds no sign zeros, no trapping math, associative math, reciprocal math. And also it does this terrible thing where it links in CRT fast math, which enables flash to 0 for your whole program. Even if some dynamic library that you don't even know that you use because it's 3 dependency levels deep has linked against this, it will change the behavior of your floating point program. It's actually not true anymore. Since GCC 13, after 15 years, this has been changed. This is no longer true. It will no longer link in this magic object file. Of course, GCC 13 is not quite as old as you might want. For example, if you are the kind of person who uses stable Debian, then GCC 13 is still the future for you, and this is still happening to you. So that's a lot of flags, like a lot of them. And actually, that's from GCC manual. Clang has more of these flags. And if you enable them, are you sure they won't break your code? Because there's a lot of changes. So again, don't use fast math. Use the individual flags after you have read the documentation and understand what they actually change. Let's look at some of them. I won't be going through all of them. We would be here for a long time, but I want to show you some examples of what they will actually do to your code and what the changes you can expect from enabling them. So let's start with fno math rno, which is the one flag that I think is actually good and you should enable this. And it says, hey, for math functions like square root, don't set rno if they fail. I won't be reading it, so don't bother setting it up. And this helps with vectorization a lot. This is an example from last month, from my talk. We have a very simple function that takes in a bunch of data and basically turns them into their square roots. Easy enough, right? And this is the assembly that we get on the left with just normal optimization level. And on the right, if we disable math rno. I want you to focus on this. This is a lot of assembly, and then we call sqrtf. We actually call the function. But there is like a lot of other stuff. So what are we actually doing? So we are also using the hardware instruction for square root of single, notice SS, of a single float in the register. So what is actually going on? Well, we start by checking whether the input that we are taking the square root of is valid. If it is bigger than 0, then we proceed to use the hardware instruction. If it's smaller, we call sqrtf to set the error number. Like, no. Now, compare this what happens if we say we don't care about rno. We will not read error number, just don't care. That's it. This is the whole main loop. We just do, we take the square roots of all floats in the AVX2 register. So we are actually going through 32 bytes at a time. This is the whole loop. We never call like into external function or anything. That's it. That's it. Done. And I want to reiterate, this is the one flag that I actually recommend using. I never cared about rno in math function. Caveat, you do have to ensure that the inputs are actually valid. If they are not valid, then something will happen. And you will probably get nonce in your data. You have to figure out like where did you get the nonce and so on. Now, there is actually one more flag that I think is reasonable. Not good, but reasonable to just enable. And that's fno trapping math, or when I'm dealing with floating point operations, then I don't care about the traps that should happen, like if you divide by 0 or whatever. And this actually allows for some reordering of floating point operations. Let's take a look at an example. This is very simple code where you just go through an array. It's global to make it simpler in the assembly that we finalize. And we check that if it's bigger than 0, then we set it to x over y. And x and y are constant in this loop, right? So in theory, we should be able to hoist this out of the loop, right? Should we?
No.
No, of course not. Because this is, again, the assembly for the function if we have just normal optimizations. And here, if we disable trapping math. Notice that the division is inside of the main loop. Why is it inside of the main loop? Because if it causes a trap, because, for example, we will divide by 0, then the compiler is not allowed to cause it if it wouldn't happen like with the different inputs, right? When we are here, if we give it an array that's all like 0 or smaller and y equal to 0, then this will not trap. So it can't move this division up top because it would trap. Now, if we tell it actually, like, I don't care about the traps, then it will do the division up top, and that's it.
I just like to emphasize one thing. You haven't tried to specify expression. Can you just show the code before? I will explain.
Yeah.
I believe that this if is also important because it dynamically affects the result of the previous version. So if we would use something like array I is equal multiplication, then how to do it? And so
What do you mean?
one line. The all math could be done in one line, and here without this if and without this comparison would be 1 or 0. So we can do mass in one line without if sentence.
Come again, what do you mean?
We could use the value of comparison like mass expression 1 or 0.
Oh, yeah.
Then multiply it to the array I, or this expression depends on the results. So the whole sentence will be calculated straightforward.
Yeah, basically, yeah. If you force this, if you force this to be evaluated, like either way, then the compiler is allowed to move it up top. Yes. Okay, so yes, so this was moved. Now, little tangent. So C floating point, not C++. This is only true for C floating point atomics. They are not allowed to expose floating point exceptions from component assignment, right? No matter what happens here, they are not allowed to cause floating point exception. This leads to some interesting code jam. Right? This is what happens if you just try to add a number to an atomic float, and it keeps going. This is what happens if you actually say, no, I don't care about the floating point exceptions. Much nicer. But that's tangent, right? This is only for C atomic float. In C++, you get basically this with both, because in C++ there isn't the rule that you can't get the floating point exception. Yeah, so that's all the flags that I think are actually useful and safe.
The compiler, for example, division by 0 should trap or not? Or is it compiler defined?
That's actually a great question. So C99 has specified, I think it is C99, has specified a pragma that allows you to tell the compiler what to care about. Last time I checked, which was around GCC 12, GCC did not respect the pragma at all. So There is one more option, which is non-portable function, like I think it's fstdx. It's a function that's platform specific, where you can tell it which things, when they happen, should trigger a trap. So for example, you can say, I only want trap on not the numbers, but don't care about the other stuff. And then you can have like, there is a different one for MSVC, and I have no idea, for example, what NVIDIA is doing.
Those CPU flags, and if you change it and not change it back at the end of your function, the rest of the code is stuck with.
Yes. Yes. If you set it and then don't unset global state, then yes, you have changed global state for everyone. It's amazing. Anyway, that's all flags that I think are useful and safe. So let's talk about the less useful and or less safe. Let's start with the no sign zeros, which is either, okay, so first, what it does is that it says, I don't care about the difference between positive and negative 0. Now, this flag is either safe, but not actually useful because your code doesn't care. Or it's useful, but not safe, right? Because this allows you to do exactly one thing. It allows you to assume that x plus 0 is still x. This is not true in floating point numbers with sign zeros, because if x is negative 0, then this is 0, not x. But if this flag on its own does give you significant performance improvements, then your code is doing something very tricky with those zeros, and you just broke it, right? And if you are not doing something very tricky with the sign of zeros, then this will not give you any speed up. And yeah, that's literally all it does. Let's talk about more flags.
Just
yes.
Silent zeros. So if you turn on or turn off this flag, yeah, it will compare -0 with +0, and it will return true. I mean, what should I do to compare negative and positive zeros and return true? Should I
just compare them? Just compare them. Negative and positive 0 are defined to be equal in floating point standard.
Defined to be
equal. Like negative 0 and positive 0 are equal. So you just, if you have negative 0, positive 0, you just compare them. It's always equal. No flags or changes needed. You actually have to take extra care if you want to separate them, because then you have to check whether they are equal and also check for the sign bit. And okay, finite math only. This says, okay, I'm going to assume that floats can be not a number, nor can they be infinities. What this does let you is assume that actually x minus x is 0, because it's not true for infinities and nuns. And you can also assume that x equals x is always true, because this is not actually true with not numbers. And this flag is actually usually enabled with no sign zeros, because it removes like those weird IEE values. And this actually helps the compiler a lot. You know, this is another example from last month. I want to get the maximum of all numbers, of all flows. Right? I say, okay, so I will start with the absolutely lowest float I can have. Then I will go to the input. And if what I currently have is lesser, I take the new bigger value. Makes perfect sense. And if we look what we get from the compiler with standard optimization flags, we will see that we get, okay, we will compare two floats in the lowest part of the register, and then we will do it again and again and again until we are done. But if we say, actually, I don't care about infinities, I don't care about nuns, I don't care about zeros, then you see that we can now actually start taking the maximum across the full SIMD register. So we are again doing 8 floats at a time. If you want the thorough explanation why this is true, or why this works, or maybe even why this doesn't work like this, then yeah, watch the recording from the last month. So what actually makes this flag dangerous? Because right now, we like it. We saw good vectorization opportunities. We can no longer check for nonce or infinities, which means that these functions, they just compile to always false. That they are empty. We can no longer find out if we have any of these values. And you can get much more interesting stuff that happens. You can find yourself with code that doesn't take either the true or the false branch. How does this happen? Well, we start with code like this. If x is bigger than y, it's foo, or else call bar. Good. Now, I can split it like this. This is still valid, right? Do we agree? I say if x is bigger than y, we still call foo. And if it's not true that x is bigger than y, we call var. Good. But actually, we might be tempted to do this as well. We will say, okay, so if x is bigger than y, we call foo. If x is smaller or equal to y, we call bar. And this is not true for IE numbers in normal case. Does this actually happen in practice? And the answer is maybe. Let's take a look at a bit of a code. Again, like the arrays are global, fixed size and stuff, so to avoid polluting the assembly with like loading them, calculating the size and so on. But what do we do? Okay, if the value in B is bigger than some constant that we care about, then we set A to B plus 1, otherwise B to A plus 1. Okay? Let's ask Clang about what do we want, what do we get if we compile it. So it gets vectorized nicely. But notice that there are different comparison instructions here and here on the right. The one on the left is both, so the first one is compare not less than, and the other one is compare less than, right? And we compare the same two registers, we put it here, and then we do some mask, morph, and so on. On the right, where we have finite math only, we use a less or equal with in the order EMM2 to YMM0, and then we use less than YM0, YM2. What happens if not a number sneaks into the inputs here? Neither. Not a number will get false flags in both of these. So you can actually find yourself with code that doesn't do either of the two branches if you start messing with finite math. And remember, in finite math, you can't check the input data. You can't assert over input data that they are not none, because that's compiled out to false. But let's move on to more fun stuff. Associative math. This says actually floating point operations are associative. They obey math as taught in elementary school. And all these are true, right? I think we would agree that these are true in math. That's not true in floating point operations, right? What does it mean for us? So again, a lot of possible vectorization that we can get, right? We get, if we have a function like this, we say, okay, we have numbers, sum them all up. After we have the sum, return it. Then if we ask GC to compile it, we get lots of single float additions. You can see that it unrolled the loop 1, 2, 3, 4, 8 times. But it always does just a single float addition. Now, what if we tell it, yeah, actually, associative math, fine. No trapping math, fine. We start adding the float 8 at a time again through AVX register. That's nice. I like this. But why is it unsafe? So who here has heard about Kahan summation? One, maybe. So it's an algorithm for summing up numbers, lots of numbers. 2, okay. 2 a little. And it gives you lesser numerical error from summing up floats than if you just do what we wrote there, the function that just sums them up all together. And it relies on ordering of operations, precise ordering of operations. This is Kahan summation in C++. We take some sum, we have this compensation, which basically accounts for the error that we introduce. And then we say, okay, so for each f, blah, 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 blah. And at the end, this gives you like value that's much closer to, that has lesser error from the rounding than if you just added them all up. But, if you look at it mathematically, the compensation factor is always 0. Why? Well, let's take a look. So compensation is defined as t minus sum minus y. T is defined as sum plus y. So actually, compensation is defined as sum plus y minus sum minus y. Well, we can move these around. So we say sum minus sum, y minus y, that's 2 zeros. So mathematically, the compensation is always 0. And yes, the compiler does have the ability to reason through this. On the left, naive sum. On the right, the Kahan sum with GCC, with associative math, no trapping math, blah, blah, blah. They are exactly the same. There is literally no change between them. Because, like GCC is, okay, associative math, well, the compensation thing, that's stupid. We don't need to do this. And then it just starts adding it all up. Yeah. I'm going to skip over the other ones, mostly because I don't want to spend hours here. And I want to talk about one more floating point related flag on compilers. And that's FP contract. If you have never heard about it, it says, hey, are floating point expression contractions allowed or not, and how are they allowed? A contraction is, for example, fused multiply add. If you see a times b plus c, this is fused multiply and add. And it can be better for both speed and precision to execute it with specialized instruction. And C++ allows floating point contractions in a single expression. What it means is that these two functions, like FMAS, the compiler is allowed to do FMA here. FMA, no, it's not allowed, because first, multiplication happens in one statement, and other statement has the addition. Now, this is pretty well defined by the standard, but, as I said, it can give different results because it skips rounding after multiply. When you are doing the multiply in your hardware, you have temporarily access to larger precision than you have in normal float or double. And by having it all in one instruction, it can do the addition for the higher precision multiplication result. And let's go back to the flag for a second. There are 3 values for it. It's on, use the language standard of just don't do contractions, and fast. Do whatever think is fast. Now, the interesting thing is that since GCC 13, I believe, it also obeys FFP contract on. Before that, it ignored contract on, because technically it's allowed to just contract to, in case that it sees contract on, it's allowed to be like, yeah, I'm not taking the opportunity, and behave like it was contract off. This is good for reproducibility. There is one little issue. GCC and Clang disagree on what should be the default. And what happens then is that if we go back to this and compile it with no extra flags with GCC, it just does FMA for both, while Clang doesn't, because GCC says, actually, I will default to FP contract fast. I will do whatever I want. While Clang defaults to FMA, FP contract on, so it obeys the language standard. Little side note to this. If you set both to FP contract fast, you will still see different behavior between them, because they will have, in like more complex cases, they will differently evaluate whether it's advantageous or not to use FMA. So let's conclude this talk. First, don't use OFAST or FastMath. No, don't do either of these. Like, yes, they will make your code go faster, but they break IEE rules in lots of different ways, and you probably don't even realize half of them or more. So if you actually need the performance, like you said FastMath, now your code is 4 times faster, look at what has changed and use the individual flags. One exception, note, this one is basically always safe, use it. Actually, if you are, for example, on Darwin platforms, which means Macs, GCC actually defaults to this because it knows that their CMath library does not use s.r.o internally. One more quick note. The reason for this is that s.r.o is actually POSIX thing, not C standard thing. So this is POSIX fault. F-no trapping math, reasonable as well. Other flags. Know what you are getting into and don't define them globally. Only do them for a translation unit or function that you actually need them for. Because you can just put this function into one translation unit, compile that one translation unit with the fast whatever, and that's it. You don't have to let it spread to all other functions in your code. And of course, beware compiler defaults. Because, for example, ICC defaults to FastMath, whatever. And that's the actual end of this talk. Now on to questions.